These are the giants of the late Jurassic, sauropods. At 50 tons, they were the largest animals to ever walk on land, defined by their massive bodies and incredibly long necks. But an organism doesn't jump straight to this size. Evolution requires a series of intermediate steps, beginning with ancestors that were likely small, fast, and agile. For decades, tracing that lineage backward in time led to a significant gap in the fossil record. At the very base of the sauropod family tree, there was simply no physical evidence of where these titans actually came from. Identifying that origin point remained one of the most significant gaps in our understanding of dinosaur history. Evidence finally surfaced in the rust-colored badlands of Argentina's Ischgualasto Formation. Often called the Valley of the Moon, this region preserves a world from 231 million years ago, deep in the Triassic period. In late 2006, paleontologist Ricardo Martinez discovered a small, lightweight skeleton here that provided the first clear look at the beginning of the sauropod lineage. Named in 2009, the dinosaur is Panphagia protos. In Greek, the name means first of the all-eaters. It is classified as a basal sauropodomorph. This identifies it as a foundational member of the group that would eventually produce the long-necked giants. This fossil captures the exact moment a lineage of small carnivores began transitioning into the massive herbivores that would eventually dominate the planet. Physically, Panphagia was a bipedal runner. It had long arms for grasping and a slender whip-like tail that acted as a counterweight. It stood just 1.3 meters long and weighed 10 kilograms, roughly the same size as a modern medium-sized dog. Its most significant lifestyle evidence is found in the teeth, split into two distinct regions. The front teeth remain sharp and pointed, classic predatory tools inherited from carnivorous ancestors. Toward the back, they become leaf-shaped and serrated, designed for grinding down tough Triassic ferns. By housing both types of teeth in a single jaw, Panphagia physically bridges the gap between two completely different survival strategies. In the lush Triassic river valleys, agility was a strict requirement. Panphagia had to move quickly through the undergrowth to avoid larger predators like Herrerasaurus. Because its anatomy allowed for such a varied diet, paleontologists often debate exactly how it spent its time. Some argue it remained an active hunter, using its speed to catch insects and small lizards. Others suggest it was more of an opportunist, scavenging scraps when meat was available while relying on plants to fill the gaps. Regardless of the specific method, its survival depended on being a generalist. While other dinosaurs were limited by what they could digest, Panphagia could eat almost anything the environment provided. This flexibility gave Panphagia a massive advantage over the apex predators of its time. Those animals were highly specialized, locked into a narrow range of prey. When environmental conditions changed and those prey species became scarce, the specialists faced mass die-offs. Panphagia thrived because it could process silica-rich plants. It was accessing a food source that its competitors simply couldn't utilize. This chart compares the total available energy in the Triassic ecosystem from prey versus foliage. The foliage line is significantly higher, representing a virtually inexhaustible energy source. Tapping into this massive energy surplus allowed Panphagia's descendants to grow steadily larger over generations. They transitioned to 4 legs to support their increasing weight and developed long necks to reach the high canopies. The long-term dominance of the sauropods was rooted in this early adaptability. By evolving the ability to process abundant resources, their lineage overcame the biological limits that kept other dinosaurs small. To see more prehistoric excavations and follow the evolution of the dinosaurs, join the Zorax herd and subscribe.